Hi, everyone. I hope you're doing well. Well, today we're continuing our discussion of quantum mechanics, and let's see where we are. Last time we introduced Schrodinger's equation, and today we're going to start using it. And you'll see that Schrodinger's equation can be used to do two kind of similar but different things. First, we can use it to see how a system evolves in time. That is, we can take a system like a free particle, described by a wave function, and then see how the wave function changes with time as we propagate it forward. The second thing we can do is investigate potentials, like the potential of a square well or the potential of a hydrogen atom, and we can figure out the stationary states or energy states of that potential. In that case, we're not worried about how the system evolves in time. We're just looking for those stationary states. And we'll develop a simplified form of the Schrodinger equation that's perfect for that application. So that's what we're going to do. Here, let's take a look at an outline for today. Very good. So today what I'd like to do is continue our discussion of 1D quantum mechanics. We'll start by quickly recapping what we've introduced, the wave function, what it means, Schrodinger's equation, and then we'll see how the Schrodinger's equation can be used to propagate the wave function forward in time. And as we do that, we'll look at the example of free particles and wave packets. Well, wave packets are free particles. Okay? This first part, well, really it will be numerically integrating Schrodinger's equation to find solutions at different times. The second thing is we'll investigate stationary states. Or time-independent states. These describe bound particles. And we'll be looking for states of definite energy. Okay? And to do that, we're going to develop a very important simplification of Schrodinger's equation called the time-independent Schrodinger equation. And in fact, much of the rest of our discussion of quantum mechanics is going to focus on this time-independent Schrodinger equation. All right? Which actually will be a simplification for us. All right, well, here, let's quickly recap what we've learned, and then we'll get started. One sec. Okay, well, here. So the first thing is we introduce the wave function, which we represented as psi of x and t. Okay? And of course, the wave function that is a function that has a value at every position in space and at every time. In the same way that most waves do. So we have to represent quantum systems as wave functions. The wave function tells us the probability to find the particle at any location in space. And in particular, the probability to find a particle in the range from x equals A to x equals B is just the integral of the absolute value squared of the wave function over that range. And for this reason, the absolute value squared of the wave function is called the probability density. And of course, quantum mechanics only gives us the probability that a measurement of the particle's location, a measurement of whether a particle is at a particular location will either find it or won't. And quantum mechanics only gives us the probability that the measurement will find the particle. Importantly, the wave function has to be normalized. That is the integral of the probability density over all values of position, x equals minus infinity to plus infinity, must be equal to 1 at every moment in time. And then last time, we introduced the Schrodinger equation. Proper wave functions in quantum mechanics must solve the Schrodinger equation. Which here we can write as I h bar times the rate of change of the wave function with respect to time is equal to minus h bar squared over 2m times the second derivative of the wave function with respect to position plus the potential energy times the wave function again. Okay? So that's where we start out. Quantum systems are described by a wave function. The wave function tells us everything that it's possible to know about the system. Even so, we don't know everything. We don't, in general, know whether a measurement will find a particle at a particular location. We only know the probabilities. Finally, wave functions must solve this differential equation, the Schrodinger equation. All right, let's stop here, and in the next video, we'll start talking about what we can do with the wave